This is coal, and this is diamond. Both are made from the same element, carbon, but they obviously have different properties, which suggests that elements can arrange themselves in different ways. In order to explain this, we're going to have to look at an ancient Greek word for uncuttable, one that you're probably already familiar with, atom. Imagine holding a grain of sand between your fingertips. It's hard to make out the details with the naked eye, but logically, the grain would have two halves, a left and a right. Let's imagine a knife small enough to chop the grain right into. Then, you could repeat the process, slicing into quarter grains and so on. Theoretically, you could do this forever, no matter how small it got. You'd always be able to zoom in and divide it in half again. The alternative would make no sense. The grain of sand would get so small that it would no longer have a left or right. A piece so small that it didn't have any size at all. It just was. The very concept of dividing by 2 becomes meaningless. It would be like trying to divide by 2 on a calculator and it replies, "Sorry, you have reached the smallest thing possible, you can't divide anymore." This is essentially the idea brought forth by Democritus, who was crazy enough to suggest the existence of the smallest object. He was a philosopher living in 5th century Greece who took the idea of elemental substances very seriously. He believed that everything was made of microscopic, indivisible pieces, or atoms, that combine to make up the world around us. Sadly, along with many other great ideas, Democritus's atomic model was shelved as the Holy Roman Empire took hold of Europe. It wasn't until the late 1700s that atoms were once again given serious attention thanks to the works of an English scientist named John Dalton. Dalton spent his free moments collecting samples of swamp gas from the local swamps. While burning these samples of gas, Dalton learned that gases don't react all willy-nilly, but they combine in specific ratios. It was as if there was only a limited amount of pieces of gas to go around. Dalton decided the best way of explaining this was to assume that there were tiny particles making up each elemental gas. And thanks to his proficiency in Greek, he was familiar with the works of Democritus and began referring to these particles as atoms. The idea, however, was not widely accepted. Dalton had a habit of overcomplicating things, and the book he published to outline his atomic hypothesis was notoriously difficult to read. His ideas were rigorous, but his explanations were boring. In 1899, the French physicist named Émile Amagat experimented with pressure chambers. He discovered that there was a limit to how far a gas could be squeezed. Once you got to a certain point, the gas pushed back and refused to get smaller. Amagat's research showed that a gas had a fixed amount of matter. This made the idea of atoms look less like a hypothesis and more like a theory, something that had evidence. However, there was one big problem, or rather, a very small one. In order to make sense of Amagat's ideas, you had to accept that atoms were tiny, unthinkably so. Imagine looking at the planet from space and trying to pick out a single grape on its surface. That's the same thing as looking at a grape and trying to pick out a single atom on its skin. If atoms were real, they would be so small that waves of visible light would be too big to bounce off of them. It wouldn't matter how powerful your microscope was, atoms would be impossible to see by definition. Scientists are in the business of testing theories once they've been established, but how could you test this one? How could you see the unseeable? The answer came from one of the science legends, Albert Einstein. It would be impossible to summarize all his contributions in a few minutes, so we'll just focus on the one paper that is relevant to this topic that made the atomic hypothesis testable rather than just speculation. In 1827, Scottish botanist Robert Brown noticed that grains of pollen floating on water appeared to move in random patterns. Einstein decided to model what is known as Brownian motion and found it could only be explained as the result of bombardment from water particles. This meant that the water particles kept hitting the grains of pollen. Einstein drew an equation that described how the pollen moved, and by introducing an equation with a measurable outcome, he changed the game completely. An idea could be debated, but a number cannot. And the motion Einstein showed wasn't random at all. The pollen was undergoing collisions from the atoms in the water. And by finding this, Einstein did for the atomic hypothesis what Lavoisier did for the elemental one. He provided indisputable evidence. There was no more argument to be had. Atoms are real. In 2013, researchers at IBM created a 60-second film called A Boy and His Atom. They took hundreds of photographs of atoms in different positions, and playing them at high speed, the IBM researchers were able to tell the story of an atomic stick figure who plays with his pet atom. This wasn't an easy thing to do because atoms are too small to even be seen. The trick to their film is that each photograph of the atoms, well, they're not really photographs. They are images obtained from a scanning tunneling microscope, or STM, a device that allows us to look at distances smaller than visible light can access. As the STM scans, it picks up the atoms like Braille and creates an image in a computer. It's a novel idea, but how can this be possible? In order to detect an atom, the STM would need to be dropping particles even smaller than atoms. And where would we find particles that are that small? Meet J.J. Thomson, a British physicist who conducted experiments to understand electricity. The precise details of Thomson's experiments are very mathematical, but the premise is straightforward. He filled a chamber with gas and connected it to a circuit which gave it power, and it generated streams of electricity through the gas. By carrying out a variety of studies on this theme, Thomson made several crucial observations. Most important was the fact that electricity moved slowly, meaning it had a mass and was made of particles, and these particles had a negative electric charge, which he named electrons. But they were notably different from other particles. For one thing, atoms that were discovered by Dalton and Einstein were 2,000 times larger, so electrons had to somehow be hidden within the atoms. Apparently, atoms weren't the smallest thing after all, they contained electrons. And normal atoms are also happy to approach each other and bond together. Whereas electrons, like anything that has the same charge, repels each other. So how come atoms didn't have this property? If the electrons within them were repelling, how were atoms neutral and able to approach each other? Thomson concluded that the atoms had to contain something that canceled the electron's charge, giving it the appearance of being neutral. Enter desserts. In many households in England, a common holiday dessert was something called a plum pudding, which is dough containing dried plums. Thomson proposed that electrons were nestled within the atom, similar to how plums are inside a dough, and this atomic dough had the opposite electric charge of the electrons. And this gave his model of the atom a rather catchy name, the plum pudding hypothesis. By the time Thomson published his works, the name atom had stuck, which is a shame because it's really misleading. What we call atoms are not uncuttable at all. They're not the smallest thing either. They're just stable structures that prefer not to be pulled apart. But science makes progress by disproving a hypothesis, not by proving it, and the plum pudding hypothesis was eventually disproven by Thomson's student Ernest Rutherford. Rutherford earned the Nobel Prize in Chemistry in 1908 for discovering that atoms could spit out tiny particles that are much heavier than electrons and carry a positive charge. To explain this, Rutherford hired the world's best experimentalist, a man named Hans Geiger, and together they developed a method to see what was inside the atom. Geiger invented an electronic counter that could detect the impacts of these particles automatically. His invention was the crackling Geiger counter used in thousands of spy movies ever since.
Here we have a Geiger counter.
In 1909, Geiger, Rutherford, and his student Ernest Marsden did an experiment to see what happens when these particles were directed at gold foil. By placing a detector on the other side of the gold foil, they would be able to tell how the particles emitted by the atom would affect the foil. The best metal to use was gold because it could be stretched into a leaf that was only a few atoms thick. For some reason, Rutherford put the detector on the same side as the emitter of the particles. And lo and behold, the detector began picking up particles even on the same side as the emitter. This could not be explained by the plum pudding hypothesis, because how could particles be bounced back by the dough? Rutherford described it as the most incredible event that ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and it hit you. There was only one possible explanation for the result. The atom wasn't a soft dough all the way through, but had hard lumps for the particles to bounce off of. The plum pudding apparently contained nuts. The nuts were clustered in one place within the atom, since only a few bounces were detected for every 1,000 particles. Rutherford called this clump of particles the nucleus, from the Latin word for nut, and it had a positive charge to hold the electrons in place, which made the electrons orbit around it like planets around the sun. Thomson's plum pudding idea was ingenious, but now it had no more evidence. But if the nucleus contained particles with a charge opposite to the electron, we have the same question as before. Why wasn't the nucleus ripping itself apart? Particles with the same charge repel each other, so the nucleus shouldn't exist at all. And the answer was discovered by another of Rutherford's students, James Chadwick, in 1932. By doing a similar experiment, he noticed that a different particle came flying out the other side, like billiard balls colliding. And these ejected particles were heavy, and they didn't repel each other, meaning they were neutrally charged, or had no charge at all. And they also acted as glue that held the charged particles in the nucleus together. The nucleus of the atom, it turns out, is made of two types of particles: neutrons, meaning the neutral ones, which had this glue property, and the charged protons, which means first because they were discovered first. Protons and neutrons form the central nucleus, with electrons whizzing around the edge. And the strangest conclusion of them all is that most of the atom is empty space. The story about atomic models isn't over, with further research from Niels Bohr and Werner Heisenberg and many others, but the popular view of the atom was finally established. In the Superman movie, Man of Steel, a young Clark Kent is told that substances aboard his ship were analyzed by chemists and found to be made of elements that did not fit on the periodic table.
This was in the chamber with you. I took it to a metallurgist at Kansas State. He said whatever it was made from didn't even exist on the periodic table. That's another way of saying that it's not from this world, Clark. And neither are you.
The periodic table is a list of all known elements, so the Kryptonians obviously had different elements on their planet than ours. And this is an idea that had been thrown around in science fiction for decades. But you can't really have hidden elements for one straightforward reason. The word atom was supposed to mean uncuttable, but it's really electrons, protons, and neutrons that fit the description of uncuttable. The word atom stuck, so we still call it that. The smallest possible atom would logically contain one proton and one electron, since the charges need to cancel out. And so this becomes element number 1, which turns out to be Cavendish's exploding gas, aka hydrogen. The next element would have 2 protons, which turns out to be helium. It wouldn't be possible to have element 1.5 because there's no such thing as half a proton. Once you get a list of all these elements, you can be sure you haven't missed anything because nature is only able to make atoms in whole numbers. So, sorry Superman, but it's just not possible for it not to be on the periodic table.
So there you have it, the story about how a dessert changed our idea about atoms for a period of time until a new model came about from new evidence. If you learned something about desserts or atoms or the universe that you didn't know before, be sure to let me know what that was that you learned by leaving a comment down below. And for more videos about science, check out these over here.